and welcome to another Gregorius Maths video. In today's video, I'm going to be talking about the Mandelbrot set being universal, and I'm going to give a general introduction to complex dynamics. And don't worry, I'm going to be giving animations as well, pictures of what's actually happening behind the scenes. Okay, what's the roadmap for this talk? So, firstly, I'm going to look at establish the basic idea of what we're studying, and some basic definitions that I might use those words throughout the talk. Then we'll look at the Mandelbrot set. So we'll look at what the Mandelbrot set is, basically. Then we'll switch our focus to the Newton fractal, which is a seemingly unrelated thing, but then we'll discover that the Newton fractal and the Mandelbrot set are deeply connected. And then, even better, the punchline is that the phenomenon that we observe with the Newton fractal and the Mandelbrot set being secretly connected doesn't just happen for the Newton fractal. It happens all the time. And we'll see that the Mandelbrot set is actually more universal, and it appears secretly in places that you might not think. And I'll even give you a guide as to how to uncover this fact for yourself. And before I go any further, I'd like to thank Vincent and Alex for their help with apart from the Mandelbrot set. I used GeoGebra for that, but apart from that, all of the animations and the photos that you're going to see are thanks to Vincent and Alex. So yeah, big shout out to you guys. So yeah, all right, let's get into the basics first. So okay, firstly, what is complex dynamics? So in complex dynamics, we look at what happens when we iterate a rational function. So that is any function of the form f of z over g of z, where these are polynomials. So we look at what happens when we iterate it a bunch of times. So what happens when we do it, and then we apply this function to the result, and then we apply the function to that result again, and again and again. We see the behavior. Does it explode? Does it converge to some number? Does it go in a loop? Those types of questions. So one of the easiest functions we could look at is just z squared. That's a rational function. So the orbit of z is the set including z itself. Z, then phi of z. Then what happens when we do phi twice, then phi 3 times, and so on and so forth. So that's what the orbit is. That's just all of those numbers. So for example, 0, the orbit of 0. Well, we start with 0, then we do phi applied to 0, so 0 squared, so we get 0 again. And then we square that, so we get 0, so on and so forth. So the orbit of 0 is just this. And similarly, the orbit of 1 is just this, because again, we do 1, then 1 squared, then that squared, then that squared. So it's always going to be 1. And so the points 0 and 1 are called fixed points because they satisfy the equation phi of a equals a. So the number -1 is called pre-periodic. So what does this mean? This means it will end up in a loop, but it doesn't actually contain the number -1. So when we look at -1, we take it -1, then we square it, we get 1. Then we square that, we get 1. We square that, we get 1, blah, blah, blah. So this part here is a loop, right? It's just 1 looping back to itself. So it's called pre-periodic because it does go into a loop, but it doesn't actually, the number itself is not contained in that loop. Now, conversely, this complex number here, so -1 plus the square root of -3 over 2, this is called periodic because it goes in a loop. So if you square it, you get -1 minus root 3. Oh, sorry, that should be root -3, I think, over 2. And if we square that again, we get back to where we started. So this is a period of period 2 because it cycles between two numbers. And then points like 2 or a third are called wandering points because either it's because they never go in a loop. So 2 will be, the orbit of 2 will look like 2, 4, 16, 2, 5, 6, and so on. So that one blows up to infinity. And the orbit of the number of thirds will look like a third, a ninth, 181th, so on and so forth. So this one will quickly go down to 0. So, okay, that's good. These are some basic terms that I might use throughout the talk. And another note is that we have points at infinity. So we're allowed to do points at infinity. So if we study this function, phi of z equals z squared plus 1 over z squared minus 1, then if we allow the point infinity, to make sense, then 1 is periodic, because when we plug in 1, this blows up, and then when we plug in infinity, we get back to 1, so it's kind of looping. So that's why if you read some complex dynamics paper, they might be working in projective space, because that includes the point infinity. Okay, good. So here's where it gets interesting. We need to look at the concept of Julia and Fatu sets. So this is where it gets interesting, because here we study at what point, so for what inputs does a small change, so if we change z a tiny bit, then is there a point where if we change it even a tiny bit, the behavior of our function, phi, will change drastically? So for our function phi, where phi of z equals z squared, let's look at 3 cases. If we have alpha between 0 and 1, then if we pick a point beta, which is also between 0 and 1, that's close to alpha, then phi will behave very similarly when we iterate it. They'll both go down to 0, and they'll both go down in a very similar way. So, okay, if we pick some alpha greater than 1, then if we pick some beta that's close to alpha that's greater than 1, it will also blow up, right? And it will blow up very similarly too. But here's the special part. If we pick alpha equals 1, then the behavior is very different. If we pick some beta very close to 1, like 0.999, that will go further and further away. That will go towards 0. And if we pick some beta very close to 1 above 1, then it will slowly but surely go up to infinity. So it will get further and further away. Whereas alpha equals 1 doesn't either. So the behavior is drastically different, even though we can pick the other input beta to be as close as 1 as we want. So 1 is very interesting, and 1 is called a chaotic point. And the Julia set is the set of all chaotic points. So the Julia set studies at what points do changes in the input small changes in the input lead to drastic changes in the behavior of the function. And the Fatu set is obviously everything else. So small changes in the input also lead to small changes in the function. Now, the Mandelbrot set asks a different question. It plays a different type of game. So the Mandelbrot set now asks the following. So the Julia set says, we're going to change the input slightly and see where the function changes drastically. This time, the Mandelbrot set says we're going to keep the input the same, and we're going to change a parameter c and see where the behavior is different of the function. So, what does this mean precisely? Now, we start with the function z squared plus c. Okay. And the condition is we start with the input z equals 0. Then, the Mandelbrot set is defined as the set of all complex numbers C such that the sequence will not diverge. So, for example, C equals 1. That is not in the Mandelbrot set. Because when we start at 0, we get 0 squared plus 1, 1. Then we do 1 squared. Sorry, that should say squared. Then we do 1 squared plus 1. That's 2. Then we do 2 squared plus 1. That's 5. Then we do 5 squared plus 1. That's 26. That blows up to infinity. But now let's look at if C equals minus 2. Now let's start with Z equals 0. Then we start minus 2. Minus 2 squared minus 2 is 2. 2 squared minus 2 is 2. And so on and so forth. So minus 2 is in the Mandelbrot set because that will converge. Now we'll look at an animation on GeoGebra which depicts this even more nicely. Okay, so here's our animation. So let's zoom out a little bit. Okay, so here's our point C. So let's take, for example, the point here, this point 0.5i. So what does this depict? This depicts the sequence when we start with when we fix C equals 0.5i. So we start with Z equals 0. So 0.5i is our first one. Then we do 0.5i squared plus 0.5i, and that gets us here. Then when we do that squared plus 0.5i, we get here. And the point is, we can see that this is clearly diverging to some point here where my mouse is hovering. So this point here is definitely in the Mandelbrot set. But now, okay, this is still divergent, right? We can see it's kind of maybe getting stuck in a loop, but it's not blowing up to infinity. Here, just about, but then it blows up. So around here, it starts to blow up. So we see this point is definitely not in the Mandelbrot set. So we can see that there's points here that do converge, and then we go very close and it's not starting to not converge. So this Mandelbrot set is very complicated, clearly. Blows up, just about converges, and so on. So now let's trace this point C. So the green ones are the ones that converge, the red ones don't converge. So over here everything is not converging, but then over here there's a bit of green. Let's go down here. Okay, this bit is green. Okay, so outside of a certain point it's mostly all red, but okay, there's definitely a interesting shape occurring. And so we see this point in green here. These points in green, these are all in the Mandelbrot set. So we're getting a rough idea of the shape, and you probably know what this is going to look like in the end. So let's put in picture 2. So this is what it looks like in the end. So if we go in any point in this gray area, we can see it's converging. And if we go outside, it blows up. And we're inside. So this is the Mandelbrot set. So this is how we get it. So remember, remember what this is the whole time. Just remember what this is. So we start with the input z equals 0, and we look at, in this case, when C is this, we look at the function z squared minus 0.28 plus 0.46i or whatever. So we look at this function where C is z squared plus C, where C is equal to this. We start with z equals 0, and we're seeing if it blows up. So for anywhere in here, it's not. But on the border here, and suddenly it does blow up. So this is what the Mandelbrot set is. Okay, so now we're going to look at something that at first seems completely unrelated to what we just looked at. So now we're going to look at Newton's fractal. And before we look at Newton's fractal, we need to look at the Newton-Raphson method. And the Newton-Raphson method is a way of approximating solutions to polynomial equations. So this is particularly useful when we're working with, quintics and higher degree polynomials, because we need to have some way of approximating them, since there's no formula that we can just plug in. So the way you do it is you guess some number z0, you guess z0, and then you iterate. So z1 will become z0 minus p of z over, sorry, this should say zn, by the way, not just z. So you iterate this function here. So let's take a look at a quick example. So if we have square root of 2, now let's say I guess it's about 1.5, then what do we get? Well, what's z1? Well, z1 is, so z0, 1.5 minus, and square root of 2 is basically just the root of z squared minus 2. So really we're approximating a root of z squared minus 2. So we plug in 1.5 squared minus 2, and then we divide it by the derivative, so 2z, so 2 times 1.5, we get about 1.42. When we plug that in, we get to z1 minus z squared, blah, 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 we get 1.41, blah, 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 and this will get closer and closer, but you can see this is already very accurate. So it's a very powerful method of approximating solutions. So that's what it is. So it's an iterative formula which allows you to approximate solutions to polynomials. So now if we look at this square root of 2 example, if we started with the guess minus 1.5, then we would not end up with square root of 2, we would end up with minus square root of 2. So we'd end up with the other root to the polynomial z squared minus 2. So clearly, different starting points will be attracted to different roots. And now this is where the fractal comes in, because the Newton-Raphson method is actually very sensitive, especially for higher degree polynomials. So here's where the here's how we build this fractal. So we color points that are attracted to a certain root in, let's say, green. Then we color points that are attracted to the second root in red. We color points that are attracted to the third root in blue. And so on and so forth for all the roots. And we call the resulting fractal the Newton's fractal associated to the function. So let's look at an example. This is the Newton's fractal associated with z cubed minus 1. So I forget which color is which, but it doesn't really matter. Let's say green are the ones that are attracted to the root 1. Then this one is the blue is attracted to the second root, and red is attracted to the third root. So what does this mean? This means that when we go on this green spot here, if we start the Newton's fractal at that spot there, then we end up converging to the root 1. But if we start at this blue spot, like nearby, then it goes to this root, zeta 2. And if we start at the red point, it will go converge to zeta 3. So at these points here, we can see that the Newton-Raphson method is very sensitive. So a very small change in the starting point will lead to a different change in the roots. So this bit in the middle, so this border here, this sort of shape that you see going through the middle, that would be the Julia set of this of the Newton-Raphson method for z cubed minus 1. And so the associated fractal is this. But now we're going to play. So just as in the same way we played a different game for to get the Mandelbrot set, we're now going to play a different game with the Newton fractal. So again, we're going to we're going to fix a starting point for the Newton-Raphson method. So we're always going to fix a starting guess, and we're going to see how that changes which root it will converge to as we vary a parameter. So this is very similar to the idea of the Mandelbrot set, if you remember. For the Mandelbrot set, we always started with z equals 0, and we saw how the behavior of the function changed as we vary the parameter c. So we're going to play a very similar game for the Newton's fractal. So we're just going to observe the behavior. Okay, so we're just going to look at the following. So we're going to look at the Newton fractal z plus 1, z minus lambda minus a half, z plus lambda minus a half. So we're going to look at the behavior of this polynomial here. And this is just a GIF showing what the Newton fractal of this polynomial looks like as lambda varies. And I'm going to say something that might seem a bit weird to you right now. The color black means points where the starting guess doesn't converge. Guess doesn't converge to a root. Converge to a root. Now, okay, not this black bit here, I mean on the GIF. So that might seem weird because here it looks like there are no black spots. And that's good news. That's good news because it means that the Newton's fractal for almost any polynomial, for almost any starting point, will always converge to a root. So that's good news. But now let's dive in a little bit deeper. Here, what we're looking at is an animation of the Newton's fractal of that polynomial that we were looking at earlier, when lambda is equal to minus 0.019134 plus 0.296783i. So a very random value. And if we, okay, let's let it zoom in a bit. If we look at the start, it doesn't look like the black points are very significant, but when we zoom in, we do see that they are there. So for some values of lambda, there are black spots. And another important thing to note is that the starting guess z0 equals 0 will always be a black spot if there are any. If any exist. So we're zooming in around z0 equals 0. So the starting guess 0 is basically the worst guess for this specific polynomial that we're looking at, because it will not converge to any root, so it's in this black area. So what we're going to do is we're going to fix z0 equals 0 to be the starting point, and we're going to look at what the we're going to look at a fractal of our polynomial that we were looking at before. And because we have fixed the starting point z0 equals 0, we're going to capture all of the different values of lambda for which it has black spots, if that makes sense. So we're looking, again, just as we did with the Mandelbrot set, at places where changes not in the starting input, because we're going to fix it now to z0 equals 0, but changes in the parameter lambda lead to drastic changes in the behavior of the function. In this case, meaning it doesn't converge to a root. And now we're going to see what that looks like. So we apply the Newton-Raphson method to this polynomial, and we make the starting guess z0 equal to 0. And then we color it in the same way. So color the point lambda. So lambda is the one that's varying now because the starting point stays the same. Color lambda green if it converges to one root, yellow if it converges to another, and red if it converges to another. But there's another color that we have to take into account. You can see these tiny little black spots. Maybe you can't even see it yet, but there's black if starting with z0 doesn't converge to a root. So we can see that there's these tiny little black spots here. Maybe you can't even see it, but we'll do a little animation soon. So, okay, so what's the game that we're playing here? So we've kept the input the same, and now we're varying the parameter. And we're getting out these small little black islands where starting with z0 equals 0 does not converge to a single root. So now let's zoom in on what these black little islands look like. Okay, so now we're going to look at a zoom into what these black spots look like. So here's where it gets good. So we're seeing the Mandelbrot set, but we're going to zoom into a really tiny one to emphasize that the fractal nature of this. So we're zooming in, and we're not even zooming into this big Mandelbrot that you can see over here, but there's a tiny little one that we're going to keep zooming into. This little black speck here is also a mini Mandelbrot, so the Mandelbrots are completely hidden, and this is just a beautiful pattern. And there we go, so there's the zoom. What the hell was happening there? This is where we get into the real nitty-gritty of why the Mandelbrot set was appearing. And the fact is that this is not an isolated incident. So we're going to see a bunch of different examples of the Mandelbrot set appearing, don't worry. But now we need to get into the nitty-gritty of what's happening. So remember that the Julia set was a study of, we fix a function and we see how it changes when the input slightly changes. So for small changes in the input, are there points where the function drastically changes? But how did we get the Mandelbrot set? Well, we fixed the starting input, so immediately we can't talk about the Julia set. Instead, we were talking about something called the Bifurcation Locus. So that means exactly how we got the Mandelbrot set. The Bifurcation Locus is the set of all points such that a small change in the parameter now, so instead of a small change in Z, which would be the Julia set, it's a small change in this C. How a small change in the parameter leads to drastic changes in the behavior of the function. So, for example, the boundary of the Mandelbrot set, so the points just on the border where it converges and it diverges, so those points on the boundary, that is the bifurcation locus, because if we change C a little bit, either we're going to change it so that it diverges, so if we go outside the boundary, but if we change it slightly and we go inside the boundary, then it's going to converge. So that border there of the Mandelbrot set is the bifurcation locus of Z squared plus C, because it's the point where small changes in C lead to drastic changes in the behavior of the function. So now let's get more precise about things. We need to look at something called an attracting cycle. So an attracting cycle is, okay, so a cycle of period n is it's basically a cycle period n is just like a loop with n numbers. So if we have a cycle of period n of a function, we say that the multiplier of the cycle is, the magnitude of f prime of z. So because we're dealing with complex numbers here, we have to deal with the magnitude. Oh, sorry, that's not why there's a magnitude, but it is the magnitude, because we need to define, because, okay, basically, what happens is when this multiplier here is less than 1, it's called an attracting cycle. So the magnitude of f prime of z, where z is in the cycle, now I think by the chain rule this is well defined, you can check that yourself, that's a little exercise. So where z is in this cycle of period n, the multiplier of the cycle is the magnitude of the derivative of f evaluated at that point in the cycle. So a cycle is attracting if the multiplier is less than 1. So why is it called attracting? Well, this is because an attracting cycle is one that for points near it will get sucked in, so they'll go closer and closer to that cycle. For example, if we look at our function phi of z equals z squared, then the cycle just 0, 0, 0, blah, blah, blah. Well, what's the derivative? 2z. So what's an element of the cycle? 0. So the multiplier here, multiplier of the cycle 0, 0, 0, is just equal to 0, which is less than 1. So it's attracting. And what does that mean? Well, that means that points very close to 0 will get closer and closer to this cycle. And that's obviously true, because when we square numbers that are close to 0, they'll get even closer to 0. So that's the type of idea here. Now, the Fatou theorem says that every attracting cycle of a rational function will contain at least one critical point. So that is a point such that f prime of z is equal to 0. So, okay. So every attracting cycle will have at least one point such that f prime of z is equal to 0. And why is this important? Well, this allows us to, we can now precisely define the bifurcation locus, and we can use this theorem to generate our own fractals. And we're going to see that the Mandelbrot set is more universal than one might think. So here's a precise definition. The bifurcation locus of a parameterized function, so okay, that's the type of function we've been looking at now, is given by the set of points such that for some C0, the number of attracting cycles at Fc is not locally constant. So that means if we look at if we look at points very near C0, if we draw a little ring, so if this is our point C0, if we draw a little circle around it, maybe this pink point here, at this pink point, Fc will have 2 attracting cycles, but then at this point here, Fc will only have 1 attracting cycle, for example. So at our original point C0, it's not locally constant because we drew a little ring around it, we tried to draw a little neighborhood around it, and we were unable to draw a neighborhood around it such that all of the points in that neighborhood have the same amount of attracting cycles. And this definition makes sense because it means that when we change C slightly, we either get one amount of attracting cycles or we get another amount of attracting cycles. So the behavior of the function is changing drastically for a very small change in the parameter C. So it makes sense. But now, using Fatou's theorem that we just saw earlier, because it's guaranteed that at least one solution to f prime of z equals 0 will be in an attracting cycle, we can strategically select our starting point to be the solution, or I should probably say, to f prime of z equals 0. So for example, if we look at the Mandelbrot set, z squared plus c equals 0, sorry, z not equals 0, z squared plus c. If we take the derivative, we get 2z. But when does 2z equal 0? When z equals 0. So this is a great starting point to start with. And with our Newton fractal, if you compute the derivative of the Newton-Raphson method associated with the function that we had, you would see that also z0, the starting point z0 equals 0, was strategically chosen such that the derivative is equal to 0. So let's look at how to make our own fractal. So we're going to start with z to the power of 4 over z squared plus c. So now we're going to experiment here. We're going to try and compute the bifurcation locus of this function. So we'll see that the derivative is equal to, so let's say fc of z is equal to this guy. the derivative is equal to 2z cubed times z squared minus 2c. The reason I'm looking to the side is because it's written on the whiteboard over there. Over z squared plus c cubed. Sorry, not cubed, squared. So, when does this equal 0? Well, this equals 0 when z equals 0, but that's not interesting because that will always just go in a loop. So, where's the other root? Well, the other root is when z equals the square root of minus 2c. Of course, we can also start with minus that, but that's obviously going to give us the same thing anyway. So, we'll start with z0 equals square root of minus 2c. And how we're going to color the fractal is we're going to say color it in green if it converges. Okay, so color the point C green if it converges when we start with the our starting point square root of minus 2c. And color it red if it diverges when we start with our starting point square root of minus 2c. And we're going to get the following fractal. Okay, so this is what the function looks like. Sorry, not the fractal looks like. And we see here, this specific area looks very interesting. So just to be clear, this is the bifurcation locus. So what we've done is we computed the bifurcation locus of z to the fourth over z squared plus c. But anyway, this part here looks very suspiciously like a Mandelbrot. And thankfully, we've got a zoomed in image. And we can see, this is just beautiful by the way, we can see that there is indeed a Mandelbrot hidden inside this fractal. And we can see the outline very clearly. So that begs the question, what on earth? So, the precise theorem which explains why the Mandelbrot set keeps appearing in these secret locations is the following. Okay, so there's a lot of fancy words here, but don't worry too much about that. For any holomorphic family of rational maps over the unit disk, the bifurcation locus is either empty or contains the quasi-conformal image of the boundary of the multibrot set for some d. Now the multibrot set is just the boundary of the multibrot set is just the bifurcation locus of z to the power of d plus c. So for the Mandelbrot set it was z squared plus c, but it could be z to the d. But okay, so we've been seeing cases where d is equal to 2 basically. Now, what does this really mean? This means to create your own fractal, you follow the following steps. Okay, pick a rational function. Rational function. Then, compute f prime of z equals 0. This has to be parameterized, by the way. It has to be a parameter c. Then what we're going to do is compute the roots of the derivative. Then set those as your starting point. And observe, basically. So, of course, we're going to look at a ton of examples of us doing this. And we're going to see what happens. We're going to see, is this legit or not? And to quote the paper for a really nice interpretation of this result, the Mandelbrot sets are thus universal, so they're always appearing. So, by the way, let's just remember something. This bifurcation locus means we change parameter. For a change in the parameter, drastic change in behavior. Change in behavior. So that means that the Mandelbrot set always, or sorry, I should probably say the multibrot set, always occurs when we ask for a rational map for non-trivial, by the way, when the solution is non-trivial. For a parameterized rational map, the Mandelbrot set, multibrot set, always occur when we ask the question, when does a change in parameter, small change in the parameter, lead to a drastic change in behavior? So it's not just appearing when we ask what happens when we change z squared plus c. Sorry, what happens when we change the c in z squared plus c? It's actually occurring all the time. So we saw it occurred with z to the fourth over z squared plus c. We saw it occurred with a Newton fractal, which is just a complicated rational function, really. And now we're going to look at some even more examples to really hammer home this point. So anyway, to quote the paper, the Mandelbrot sets are thus universal. They are initial objects in the category of bifurcations, which I'm not sure is a specific term, but if anybody knows, then let me know in the comments. I love this part of the sentence, providing a lower bound for the complexity of the bifurcation locus for families f of t. So the Mandelbrot set provides a lower bound for the complexity of the bifurcation locus. So what does that mean? That means when we compute it, we're going to at least have the Mandelbrot set, but there might be even more beautiful patterns. But the Mandelbrot sets will always be there. So that's at least as complicated as it can be. There's no upper bound. That's the minimum amount of complicated it can be, which means it's always going to be beautiful. So, of course, I had to ask my friends to compute some of them for me, and we're just going to go through the various ones that we have. So, enjoy. So, the first example we're going to look at is the function z to the fourth minus c squared z squared over 2. So, our parameter c is here. Now, the derivative is z times z plus c times z minus c. So the interesting root that we want to look at is z0 equals c. Of course, it will be the same thing if we looked at minus c, because we'll end up with the same thing. So when we color it by doing red equals diverges, red equals diverges, green equals converges, we get this fractal pattern. Now, if we zoom in here, it looks suspiciously like a Mandelbrot, and the reason for that, I'm hoping that you've clocked by now, is that it is a Mandelbrot. And when we zoom in, we see this. We get the Mandelbrot set. If I zoom out a little bit, hold on a minute. Zoom out, please. Yeah. Okay. Yeah. That's good. Yeah. So we see the Mandelbrot set is again occurring over here. So if we take a look again at this, that is, I'll just zoom in, that Mandelbrot set was occurring over here. So that's z to the fourth minus c squared z squared over 2. Now, okay, we've chosen this rational function now. So z squared plus cz plus 1 over z. So the derivative is 1 minus 1 over z squared. So we'll start with z0 equals 1, and we end up with this fractal here. But now, when we zoom in on, what part are we zooming in on? This part here, I think you've guessed what it is. Of course, it is a Mandelbrot. And it might look slightly different than a normal Mandelbrot, but that's because it's, in the theorem it said quasi-conformal image, which means it might be a little bit stretched, but it still is the Mandelbrot set. It's just a little bit stretched, maybe. So, there we go. Again, it's occurring again. But I feel like I'm choosing functions where the derivative only has one root. So let's choose one which has two roots now. Another example. So this time we looked at the function z cubed over 3 minus 3z squared over 2 plus 2z plus c. So the derivative is z minus 1 times z minus 2. Now, how do we color this fractal? Cyan, the color cyan, is both converging. Green is z0 equals 2 converges, so starting with z0 equals 2 converges. Blue is starting with z0 equals 1 converges, but the other one doesn't. And black is both diverge. So, what we see here, this isn't a Mandelbrot, but if you look on Wikipedia at the multibrot set, you'll see that this is precisely M3. So this is the multibrot set. So this is the bifurcation locus of Z cubed plus C. And again, it looks really cool, especially with the coloring. I really love how this has been colored. So that's another example. And I've got one final example in the cooking for you guys to see. And hopefully this has piqued your interest. You'll go away trying this out, for yourself. For our last example, we looked at the function z to the 4th over 4 minus 2z cubed plus 11z squared over 2 minus 6z plus c. And the derivative is z minus 1, z minus 2, z minus 3. And again, we color in based on which roots converge, which starting points converge, which ones diverge. And we get a slightly deformed, but still, it's definitely a Mandelbrot set. So hopefully this talk has piqued your interest on the Mandelbrot set a little bit, on complex dynamics in general. And I think it's just really cool that the Mandelbrot set isn't just a really cool set that appears when you do that z squared plus c thing that you might think, but actually it's a universal, it pops up universally. So it's a universal solution to the question, what happens when we change it's a universal solution to the question, where does a small change in the parameter drastically change the behavior of the function? And it's always there for rational functions, which I think is really cool. And it, again, as it said in the paper, provides a lower bound for the complexity. So it's just the starting point for how complex these sets can be. So yeah, hopefully that's really interested you. And thank you guys for watching, and I'll see you guys in the next one. Goodbye.